Good evening, ladies and gentlemen. Welcome to the fourth presentation in the 2007-2008 Linus Pauling Memorial Lectures. My name is Terry Bristol, and I'm the president of the Institute for Science, Engineering, and Public Policy. The Institute organizes this in partnership with our co-sponsors, and it's my pleasure to mention and recognize and thank the co-sponsors. First, our main corporate co-sponsor has been for several years, and we love them, Mentor Graphics Corporation. Yay. And then listening to Oregon Episcopal School as a co-sponsor. Thank you. FEI Company, Lewis and Clark, Pacific University, Warner Pacific. Thank you. Oregon University System, which is a chancellor's office, major player. Portland State University, Western Oregon University, Portland State, okay. Western Oregon University, ONAMI, which is the Oregon Nanotech initiative, and that's where all you guys are all your jobs are gonna be in the future. They're down at Oregon State. Portland Community College, major player. Thank you, guys, yes. And Clark College in Vancouver is there. They're right. And Mount Hood Community College. And who might I... And then a lot of the students that are here, the high school students, are here because of separate from Mentor Graphics Corporation, Mentor Graphics Foundation gave us a grant that we matched, and it allowed us to subsidize the heck out of tickets for the high schools. And so a special thank you, particularly all the high school kids are here, for Mentor Graphics Foundation, yeah? Okay, then I got this thing here. One is we do have the zero tolerance on your cell phones, and zero tolerance means there is this laser thing that they've set up. I'm not sure where it's located, but if your cell phone goes off, or you hear a cell phone go off near you, get it spread away because they're getting. Anyway, so check your cell phones anyway. And okay, and ba-doo. And the questions, so after Dr. Kosko's formal presentation, then we'll do the questions. Most of you know this as usual, there are 3 microphones there, and we'll rotate that. And then the biggie here, you may notice there's this mysterious, we thought it was blue, but it's actually green sheet in your deal. Now this is primarily for the students. It's not primarily. Well, if you're a student, if you take the moment to fill this out, and if you don't have a pencil, the ushers have pencils. And if you fill this out, there is, and hand it in. You can either hand it to the ushers, or there's some boxes as you go out the door or in the lobby there. Hand those in, and if you're a student, a registered student at either a high school, a community college, or university, there's a drawing, and it happens in 4 days. This is not, you don't have to wait forever. 4 days, you're going to draw for an iPod Shuffle. It's a little incentive to take a minute to fill this out. This is important because this is it's probably the chancellor's office, but it's sort of like everybody, there's some tax money in this, and so we want to be like super accountable, and the university system wants to know that this is stimulating you high school students to go into science and math and be inspired. And I'm not really coaching you on what to say on this, but the other thing we're supposed to be really interesting is we want us to track whether or not this inspires you to stay in Oregon and go to Oregon campuses, which is actually a good idea because they're cheaper than going to other obscure universities that are not as good anyway. There you go. Anyway. Okay. So, and then if you're not a student, still, I would like your feedback. If you have any suggestions, say, have you thought of inviting so-and-so, that sort of thing, or would you not talk so long at the beginning and things like that. You can say any of those things that you like, and we will listen to them. Okay, so be sure and do that, and that'd be a big help if you would do that. And finally, for this evening, it's my pleasure for introducing Bart Kosko is George Lenderas, who's a professor of systems science and electrical engineering at Portland State. He's also the acting director of the Systems Science Graduate Program, which is a great program at Portland State, has been for years. And also he's the director of the NW Computational Intelligence Lab. Cool. So he's been around for a long time. He's one of the real intellectual assets of the state of Oregon, and he's been up there at Portland State for a while. So help me welcome George Lenderas.
Well, thank you very much, Terry. It does really give me a great pleasure to introduce this evening's speaker, Dr. Bart Kosko. He's a professor of electrical engineering at University of Southern California. Gosh, this guy, he holds degrees in philosophy, in economics, mathematics, electrical engineering, and on top of that, he's a licensed California attorney. Now, he's the author of a variety of books. One of them is this book, Noise. I got myself a signed copy tonight, which is the basis of the talk we're all going to hear from him this evening. But in addition to that, there's an important book, several important books, the one entitled Fuzzy Thinking, another one, Heaven in a Chip, a novel called Nanotime, and several textbooks and edited volumes that deal with fuzzy logic and neural networks and intelligent signal processing. I know I've been teaching courses in what's now called computational intelligence for almost 20 years now. And in the early years, in fact, I used several chapters in manuscript form of Bart's book that he had on fuzzy systems in my neural networks class. So his writings, other writings have appeared in the Los Angeles Times, the New York Times, Scientific American, and other venues like that. And in addition to all that, he's an award-winning composer. So those of you, I understand that about half of you here, I can't really see you, all I see are the lights, but about half of you here are students either at high school or up through the university system here. And I encourage you to go to his website and see the bio that was done there based on an interview from the IEEE Spectrum some 10 years ago. But I say that for you to use that as an inspiration for how you go in developing your own intellectual pursuits the rest of your life. Because Bart really is what I would consider, I use the label Renaissance man, or what we mean by the word Renaissance man is a person who has wide interests and is expert in several areas, and Bart really qualifies there. And so I will just close in saying that I believe that he's an outstanding intellect who has made original contributions in a number of different areas, and this is in science, in engineering, in literature, theater, and in music. Bart?
Wow. Thank you, George.
You're welcome.
Thank you. Wonderful. Thank you. Thank you. It's good to be back in Portland. The last time I was here was 1995, discussing fuzzy logic, which was a kind of garbage bin technology, something that for many years had been looked down upon, and in much the same way, so is noise. Indeed, noise is very much the new chaos, or like chaos, something that we've dealt with largely in the negative, and those of us like Professor Lindaris and myself who work with this professionally have spent a lot of time trying to cancel noise, eliminate noise, and the like, and found out along the way that sometimes noise is a good thing. So the structure of my talk will be an introduction to this ubiquitous concept of noise, this new chaos. First, how it's bad. For example, cell phones going off during the midst of a lecture. And shading in some insight to how it's good. And afterwards, I hope for some vigorous questioning, so please come up with some questions as we go. First, what is noise? The general answer, noise is a signal you don't like. We have to define signal, and I'll do that in a moment. Whether you like it or not, well, that's subjective. And one of the problems, of course, like with that cell phone, is one person's signal is another person's noise. And we have a lot of unanticipated third-party effects with modern gadgets and an increasing problem with noise and noise pollution. The Noise Pollution Clearinghouse, which I have quoted here, is one of many organizations concerned with noise as an increasing form of urban and technological pollution. Besides chemical pollution, the atmosphere and the oceans, increasingly of the digital sphere of your internet screen is the pollution of noise. And in particular, it has an origin from the Latin word nausea, and it comes from and involved in many processes. Here listed leaf blowers. There's something like 90 million leaf blowers alone in this country, to give you some sense of the noise, and a variety of other gadgets, all of which increasingly get more powerful, impose more cost on those around us. What is a signal? A signal is anything that conveys information. It's also anything that has energy. From a more technical point of view, so we have a lot of students here, a signal is something you would write in science with the variable x. And when X changes, X could measure the voltage, X could measure acoustical energy or anything else that would be a signal. So noise is a type of signal, and again, one person's signal can often be someone else's noise and vice versa. We call that the signal-noise duality. White noise, we'll talk about, there's many forms of this. White noise, it means the hisses and pops and the static you hear on the radio are technically independent in time. In the same way in which if you flip a coin in an ideal way, each flip is independent of the other, and knowing the outcome of one flip would not affect your knowledge of the outcome of the other flip. One of the most famous and deepest and biggest examples of noise is a noise that's shooting through your body and brain right now and the entire universe, the leftover ringing of the bell from the Big Bang, which took place on the order of 14 billion years ago. I think the best estimate today is 13.7 billion years ago. And as you may know, there was a Nobel Prize given out, shared by two folks at Bell Labs, who first detected with a very careful instrument device noise in all directions. No matter which direction they pointed the measurement device, there was still a very faint noise, and it tended to correspond with the predicted noise that should be left over from the big fiery explosion, from the Big Bang, from the time when the universe was smaller than a quark, which is hard to get your mind around. Now, if you look at this Mercator-type projection of the known universe, which comes from a NASA plot, you can see that online if you go to NASA, you can see that it's not uniform noise. And a lot of what we are as a universe, what we are likely to become, depends upon the non-uniformity in this noise. There's something called the WMAP, Wilkinson's map satellite right now that took this, looking at this. The Europeans in July are scheduled to launch the Planck surveyor to really do, among other things, look at the noise within the noise, these tiny ripples. A different ripple in that noise could indicate a different potential future in terms of star formation or star death and a variety of other things. But this is the world as we know it. Tiny waves of about 2 millimeters are passing through and around everything. And in the end, the universe appears to end in noise. Given the measurements we have from WMAP and elsewhere, it looks as if the universe won't collapse in on itself. I'm certainly not an expert in that field, but in the book Noise and elsewhere, I've done some research on it. And the current estimates are that the universe simply runs out of gas. Things will get bigger and colder. Eventually, stars will no longer form. There may be nothing at the end except several black holes. And it turns out they too emit noise, something called Hawking radiation, after Stephen Hawking. And by emitting noise, they run themselves out over time. And in the end, so far as we can tell, there is, not to end on or start on a depressing note, but there'll be a cold death of the universe, where there's, if you think about this, there's nothing left at the end except a very faint noise in a much bigger universe right above absolute zero, with potentially no memory of any event that came before. Well, that's just what happens if the physics of today unfold as we think it will, but it may very well change. We'll talk about noise from a different point of view, in the homegrown sense of the law. Noise has a long history in the British common law, in our system, and the civil law system of Europe. It is a tort. It is a civil kind of wrong. It's a nuisance. It can be a private nuisance or a public nuisance. Formally, it's a substantial and unreasonable interference with the use and enjoyment of your property. And that property could be your apartment, it could be your house, it could be your factory. And it's one of the thorniest areas of the law. It's very complicated in terms of how to litigate, how to defend against nuisance. Most of us impose nuisances on others. You don't always win. You can win your case in the law and the judge may still not agree to it. It's been the subject of vigorous scientific analysis from the branch of law that I work with called law and economics, where we attempt to reduce the law to science, in particular to principles of economics. And here you would distinguish a nuisance from a trespass. If you live next to me and I play my stereo too loud, that's a nuisance. But if I throw dirt clods on your property, that's a trespass. If, continue in a fuzzy way, very tiny dirt clods, it's still a trespass. If I throw very faint dirt clods or dust at you, I transition from a trespass to a nuisance. And it's actually a different body of law that applies in this case. And it's a thorny issue. And what the result is of a lot of research in the last 30 years from the branch called Law and Economics, which looks at to what extent the law is efficient. In other words, if we really were to design the law in some ideal mathematical way, and there are a lot of people who look at that, would we get the kind of laws that we have? Would we have the laws for contracts, basically enforcement of promises, the basic laws of criminal behavior, against criminal behavior, the laws of tort, and so forth? The answer is largely yes. It's not a completely settled question, but on the distinction between, at the noise level, between a trespass and a nuisance, it is this. If the transactions costs are high in a case, it's much more likely to be viewed as a nuisance, and it has a different body of law. If it's low transactions costs, then trespass. So if you're walking across someone's yard without their permission, that's fairly straightforward. Who owns the property, who doesn't? If you're playing your music too loudly, and I know you wouldn't do that, good citizens that you are, and you keep your noise to yourself, but if you were, who owns the sound waves as they percolate out in a sphere? Well, you or you're responsible for them. It's very difficult to try to litigate that. I mean, in theory, in an ideal law and economics scenario, each person would run around forming contracts with everyone else about the various noise levels they impose on each other. Obviously, that's too difficult to do because the transactions costs are high, because it's awkward to ask a neighbor to turn it down. As a consequence, we deal with that as a nuisance, and the law tends to look at that and says a rule would be better. Rather than to have, even in an ideal, perfectly free market style society, rather than to have these contracts, it's better to have a rule, a rough rule that gets it right on average, just because of the difficulty of litigating that. Now, over time, that perception of the law has evolved into zoning ordinances. In fact, if you look at the history of zoning ordinances for noise and for many other things, they really come out of the early part of the 20th century dealing with piggeries, someone putting a pig pen next to your property. As urban folk interacted more with rural folk, this tended to happen, and it was a lot more efficient on this view simply to have rules. The rules became laws. Locally, they become ordinances. I'm sure Oregon has an enabling act in the state that permits this, and every major city has noise ordinances, and I really encourage you to go online and examine Portland's to see what they say. And then it goes further from that. At the federal level, again, because the property rights break down, because they're too fuzzy, who owns what, and because we tend to have a lot of third-party pollution, noise pollution, there really seems to be no efficient way to do this other than through a government, some kind of federal operative, and that's led to the rise, as you know, of the administrative agencies to enforce laws involving the environment. In other words, it's too difficult from an economic point of view to every time there's a noise violation at the atmospheric level of an airplane flying over for you to litigate that. It's easier to have people who are dedicated experts with a job to do that, and thus arises the administrative agencies with all their pluses and minuses. All the way up till ultimately we can view global warming as a kind of noise or interference with signals we like, for example, clean air, cleaner air, and that kind of thing. So there's a long, rich tradition of noise and the law of nuisance and the relationship that we have of people over people in the very structure of governments. And that's only going to increase as there are more people, we live closer together. The physiological effects of noise to first order almost always negative. There's a lot of high-risk activity going on out there with iPods and other devices. In some sense, society is a little less noisy. Because of regulatory agencies, airplane noise has been reduced, car mufflers are better, and more people wear headphones. In other cases, it's much higher. For example, in hospital lobbies and hospital rooms in general, the measured noise levels are much higher than they used to be. But the overall effect of increasing energy or noise in your ear is to damage, over time, the inner ears. And you can think the inner ear hairs. Those inner ear hairs, there's a picture of it here on the lower right amplified, a clump of them. You can think of them as a comb, a nice comb that you comb your hair. And each tooth in the comb codes for a particular frequency, up to about 20,000 cycles per second. It's about the upper bound in hearing of high frequency. And every time you get a bump in the head or expose your hearing to too much noise, or just to the effects of age, or you took the wrong antibiotic at the wrong time, or 100 other factors, some of those hairs bend and sometimes they break. They ultimately have the job in that pathway of converting the energy, the mechanical energy from sound, like you're hearing from my voice now, into electrical impulses in your brain. And it happens by opening and closing ionic channels. And sometimes those channels are left open, which may be one of the causes for tinnitus, constant ringing in the ear that many folks have, and it can be quite extreme at times. And in general, for a loss of hearing. And the problem is, once your hearing starts to go, once those teeth, and they will in time, but the question is at what rate, once those teeth on the comb start to break, you don't know it, it's irreversible. And what you tend to do, especially if you're listening with headphones to a lot of music, you tend to up the volume to compensate for that decrease in the hearing, and that has a feedback effect. You up the volume, you break more teeth, and before you know it, we have this JAMA study at the bottom of the page. Now, this was 10 years ago that the Journal for American Medical Association examined a large set of American teenagers. This was before the iPod and a variety of other inexpensive but very powerful devices in terms of the decibels that can be injected into the air canal. And they found that about 15% of American teenagers have hearing damage on the order of quote unquote old folks, okay? And it has to be higher today. So if you're listening to an iPod or some kind, I don't want to pick on the iPod per se, but any kind of headset, you've got to be very careful. That is high risk activity. I'm not a physician, can't give medical advice, but general knowledge of it is you should have that hearing checked every year or two. And I would think twice before having children do it in terms of the long range effects on hearing. Now, if you look at this chart, it's a standard chart on measuring the intensity of noise or sound in terms of decibels, 10th of bells after Alexander Graham Bell. And the upshot is human, every 10 decibels here, we go by a factor of 10. Human speech is on the order of 60 decibels. And if you see on the left, the maximum exposure, when you get near 90 decibels, a power drill, shop tools, do that for too long, and you almost surely will have some kind of hearing loss. Jet takeoff 1,000 feet at 100. If you're near a rock band, typical live rock music studio, or other studies have shown if you were right here during the playing of classical music, that can cause severe damage with a relatively short amount of time. The air itself limits how much noise you can project into it. Here it's listed about 194 decibels. Beyond that, the particle structure, the gaseous structure of the air doesn't really transmit sound. That's very much unlike water, which can go much beyond that. Water is much more efficient at transmitting sound than is air. Now, something that has emerged in Europe and is yet to take on here, and if there's a social activist angle to this talk, it is this slide. Every city should have this sort of thing, a noise map. Do you know the noise map for your neighborhood? Do you have a kind of contour map of what's loud and what's quiet? All the major cities in Europe have this. You can check them online. I did notice in some research that Portland has some noise map data, a very limited study for the downtown area, but still not a general kind of noise map that you would find in the case here of London or in Paris or in many other places. It obviously could affect where you live. It could affect the overall rates that are charged by renters or by landowners and by landlords, and also by developers and overall effects. And the city may very well want to regulate that. But this is a kind of thing, whatever your theory of government, it's hard to argue with disseminating this information. It's relatively easy to measure. Noise devices are inexpensive. You can buy them at the local electronics store. And this information, actually, it's not too difficult to put together and publicize. But if I were in Portland and I went to a city council meeting, one of the first things I would ask them is, where is the Portland noise map and how frequently will you update it? So that's something to bear in mind, a walk away thing. So besides the noise that we impose on one another and the many problems that causes, hearing and problems with lack of sleep, there was, one mentioned this in the journal Nature, some anecdotal evidence that late at night in Paris, a single motor scooter driving very late can wake up 200,000 people. If you think about the cost-benefit ratio of that, there's a benefit being obtained by the person on the scooter, but at the cost of waking up not thousands, but hundreds of thousands of people, it's all out of whack. And this is that market structure of noise as a nuisance, of a third-party effect or a market failure. And we're noise polluting the environment. Now, one of the first studies to show this, a couple of them, the one here from Europe, about songbirds in Europe living too close to various noise centers, that the birds had to sing at higher frequencies and emit more energy to maintain the same signal-to-noise ratio. Now, they're not adapted for that. And it's interesting to imagine what over time the effect it's going to have on a lot of species at that level. The effect here I call it a kind of cocktail party effect. I'm sure you've noticed it. If you and I are in a discussion at a cocktail party or at a restaurant, we have a certain signal level between us, and everyone else's discussions, their signals are noise for us. So we have a signal to noise ratio. As it starts to get louder, in order to maintain the same signal to noise ratio, you and I have to speak louder. But as we speak louder, other people have to speak louder to counter us. And we get this collective failure of the noise problem. And over time, what happens is you maintain roughly the same ratio, but the absolute level of the noise just goes up and up and up. And that's what scientists observed with songbirds. And a more controlled experiment took place a few years ago at sea, where scientists, biologists worked directly with the Navy. And I discussed this at length in the book Noise, which has about 100 pages of endnotes, something authors love, publishers hate, but they're in there. Feel free to consult them for the primary source material. When the Navy turned on its very controversial low-frequency sonar that the Navy claims it needs to detect ever quieter submarines, the effect was that humpback males had to sing a lot longer, 20% average, and when the Navy turned it off, it stopped. They went back to the before. So it's a pretty good, and they did that a couple times, pretty good cause and effect estimate in that case. The problem with noise in the water is, again, that water is almost a perfect fluid, an ideal fluid. It has a lot of nice mathematical properties. It's incompressible for all practical purposes. It transmits sounds much better than air. For example, on average, sound travels and noise travels about 5 times faster in water, depends upon the temperature and a variety of other things, and it goes much further. So this talk is decaying very quickly if we open the doors outside the building, but if I were doing the equivalent talk underwater, I could go for miles and miles, the signals, and maybe well beyond that. Humpback whales can communicate what appears to be for hundreds of kilometers, or for many, many miles, maybe hundreds, depending on how they measure it, unlike other creatures. If you're evolved underwater, your main sense organ is pretty much sound, or based around sound. It's not sight. You can't see. Water is very much occluded, but sound is very different. For example, a shark, and I'll have a picture of one in a moment, a shark is like an ideal signal processing device. It can detect a very faint flutter of a wounded creature on the order of a mile away, just by a few faint vibrations in the water. Now, if you run a boat nearby, if you have a depth finder, some of these modern depth finders have the effect, if you're near them underwater, of almost being near the takeoff of the space shuttle. Very large decibel numbers on the order of 180 decibels. At any given moment in the ocean, there's on the order of 1 million boats out there, most of which have depth finders. So the ocean's gotten noisy. It's in the same way, at any given moment, there's about 100 lightning flashes right now as we speak around the world, and that produces a kind of atmospheric noise that astronomers have to worry about. But the measurements of the ocean have shown in the last 40 or 50 years that the ocean is at least 10 times noisier than it used to be. So we know we're polluting the ocean chemically. That's just common sense and gravity, increasing runoff from all the nations of the world. But we're also polluting it in a noise sense. And one effect has been to appear to damage many species. In some cases, for example, in drilling for oil, various air guns are used that have a decibel level on the order of 230 decibels. You couldn't even achieve that in air. And afterwards, squid and all kind of other fish come floating up and the like. In particular, the most famous example of this is the beaked whale. The beaked whale is the deepest diving of any mammal. And there's a great deal of controversy about this. A few years ago, the Navy was experimenting, or testing rather, its low frequency and intermediate frequency sonar, which again it needs, or claims to need, to detect ever more quiet submarines. And about 4 hours later, several beaked whales washed up dead, in effect bleeding from their ears, as you see here. The Navy claimed there wasn't a direct causal relationship, even if it were due to low frequency energy. It could have been due to a landslide or a lightning bolt or some kind of other phenomenon in the ocean. But this has occurred more than once. When the Navy experiments at a high energy level with this sonar, about 4 hours later we get dead whales washing up. Another example was the Spanish Navy did this in the Canary Islands, and about 4 hours later dead whales washed up, beaked whales. Now, you may or may not have heard, there was a lot of litigation on this point here in the Ninth Circuit. Oregon, like California, is in the Ninth Circuit. The Navy wanted to do more, in effect, war games off the coast, I don't think of Oregon, but of California, especially San Diego area up to LA and the Channel Islands. And a lot of environmental groups brought litigation to oppose that. There was a preliminary injunction to prevent the Navy. It went up to the Ninth Circuit. It went back and forth. In earlier part of this month, the judge, local district court judge in California, did reinstate her injunction to prevent the Navy from doing this. And 2 weeks ago, almost 2 weeks ago, President George Bush reversed that. And it's interesting, just from a legal point, as a separation of powers, whether he could really do that. He did it, and the Navy's doing the experiment, I guess, as we speak here. And there's an appeal going underway, but the extent to which the executive branch can interfere, in effect, with something spawned of congressional legislation is itself very problematic, but it's highly litigated. Some of the claims may be too extreme. It's not clear that all sonar hurts sea life, although no doubt it does some extent. It's pretty clear that the low-frequency sonar does, and you're looking at an example of it here. Now especially for the students out there, give you a little more technical talk about noise. The word white noise, look, there was a movie called White Noise, wasn't there, a couple of years ago? There was an award-winning book by Don DeLillo called White Noise. And it's a word that's bandied around quite a bit. First thing to learn about white noise is that there's infinitely many kinds of white noise. The most popular kind, and especially in the classical books of physics and engineering, is Gaussian white noise, or white noise described with this kind of bell curve you see in the upper left-hand corner. Now, what that bell curve says is that it's more probable to get a noise spike near zero, right at the center, and as I move away from zero, it becomes less probable in proportion to the height of that bell curve. If I look to the right, I see actual noise samples, the hisses and the pops of Gaussian noise, and it jumps back and forth between 5 and -5. Below that is the uniform probability distribution. This is what we mean when we say something is equally likely. So in the range from whatever it is here, 2 to -2, at any given moment, it's just as likely that you'll get a noise pulse from one place as from the other. It generates white noise, and that white noise looks like the plot here in the middle. Again, what white means is that each time I flip the coin, it's independent of the previous flip. Each noise pulse is independent of the one that went before it. Beneath that is something called Laplacian noise, also from a famous French mathematician and physicist. Laplace noise, often found in image processing and various radar systems and a variety of other applications in engineering and detection of faces and image detection. It's a kind of a steep bell curve where it concentrates the probability over zero, and you can see its noise in the lower right-hand corner looks different than the Gaussian noise on top. It has a few more spikes and not quite the same structure. If the hisses and pops are not perfectly correlated, well, they can't be, because if they were mathematically, you'd have to have infinite energy. We say that that noise is colored or non-white. It's correlated noise, and over the years there's emerged a classification scheme that looks something like this: pink, brown, and black noise. There's even a rock group now, I understand, called pink noise. I'm not quite sure what the adjective means in that case. Here, pink means that the noise, when we look at its frequency, the thing plotted on the right, you see a sample of it on the left, and then to the right you see its spectrum, and it's falling off. Now, if that were ideal white noise, it would be flat, in analogy to white light, equal energy across all the frequencies. But it falls off in a relatively mild way. The ear actually hears, for a variety of reasons, pink noise as white noise. And if you listen to the pink noise next to white noise at the same intensity, the pink noise is softer. Brown noise is softer still. It arises from a variety of physical applications that come out of diffusions, a lot of chemistry applications, and the name really refers to what the noise paths look like, what are called sample paths. If you look at this plot here, it looks like a Brownian motion, something it's continuous but has infinitely many corners, something jittering randomly. And it has a spectrum, but its spectrum is a little steeper. It falls off a bit faster. And black noise has an even steeper spectrum, falls off even faster, and it would sound even softer. There's a lot of debate in physics, in biology, and elsewhere of the extent to which pink noise really exists in the universe, or the extent to which we can model this, what's called a power law, or often called a fractal. They're all of a piece. In some sense, of pink noise and brown noise are types of fractals. In this sense, if I took this brown noise plot and zoomed in on any piece of it, it would look up close just like this plot itself. And if I zoomed in on that piece, it would also look like Brownian motion all the way down to infinity. I would never zoom in and get something that looked like a line. It would always be jittering. Pink noise means that if I'm flipping coins that say, for example, after 3 heads in a row, it's going to be more probable that I get a tail on the next flip. That would be a very soft kind of correlation. Now, this is almost certainly the case inside electrical circuits and computer systems. It's often called popcorn noise because if you put it to a sound device, it sounds as if you dropped a lot of BBs inside a lead can. It's also called flicker noise and a variety of other noises outside the thermal effects that take place in a chip. When, for various reasons, electrons are colliding in special ways to produce pink noise. The other applications are controversial. One of them is, for example, that the fossil record of animal life on the planet obeys a pink noise structure. This is why I said at the beginning that noise is very much like the new chaos. We're seeing it everywhere now and looking more deeply into its structure. So how could it be, though, that species extinctions over hundreds of millions of years are correlated? No one's proposed any mechanisms, but if you plot out the data, you get a pretty good fit. And that suggests some kind of mechanism that we just haven't found. But that debate continues. Here I'm going to go back to the white case where the coin flips are completely independent and make another point. You've all heard of the bell curve, and there was a book called The Bell Curve about 10 years ago in terms of IQ distributions. You've got to be very careful with that. I once had a chance to have a discussion with the author of The Bell Curve and pointed out that the title of the book was an error. There are infinitely many bell curves, and you're looking at two of them, and to the eye, the curves on the left, they're similar. They both have a bell, they both taper off in tails, but the so-called Cauchy bell curve. Cauchy was a famous French scientist, mathematician in the early 19th century, the dual in many ways to the famous German mathematician, scientist Gauss, Carl Friedrich Gauss. And they both have their own noise and their own kinds of distributions. But in the Gaussian noise case, which is what most physicists still assume, and I stress the word assume, you get nice, well-behaved noise. But if I take a bell curve that's very similar to this, but slightly thicker tails, I get noise that's extremely impulsive, like lightning bolt striking. So if you look at the scale, the curve in the upper right, it goes from plus or minus 5. On the curve at the bottom, it goes plus or minus 400. In other words, at that level of Cauchy noise, brought about by slightly thicker tails, if I plotted the Gaussian white noise, it looked like a straight line. And one of the big revolutions conceptually in modern engineering and physics has been to get away from Gaussian noise in the relatively simplistic model, even if we assume the noise is white, and start dealing with the case where the curve's a little thicker. Now, that means, among other things, that what we might have earlier said was an error or a so-called outlier, a statistical outlier, really may not be an outlier, really may be a pattern. It's an outlier in general only if you assume the very curve at issue, which you have to test for, the Gaussian. And that brings up a cautionary point, especially for you students. Many of you might have heard in a stats class long gone of a quantity called variance. It is a way of measuring the dispersion about a central point. But it is not the only way, and it has all kinds of mathematical problems. It was just a popular way 150, 200 years ago for a lot of technical reasons. It basically made the math easy. But it comes at a very high cost of ignoring what we call infinite variance cases. Now, I want to make a point here. Look at these bell curves. I think you'll agree to first order, the bell curves at the top. It's pretty hard to distinguish these. And yet, slight changes in the tail thickness, which describes the probability with which so-called rare events will occur, lead to radical changes, qualitative changes in the patterns of noise and signal. If I look at the four noise plots here, the first one is the classical Gaussian Brownian noise. And again, I'm between plus and minus 5. But as I lower the parameter alpha here, goes from 2 as Gaussian, lowered a little bit, like to 1.8, I get much more energetic spikes. And if I lower it still further, 1.5 and all the way down to 1, I get massive energetic spikes. And there's a whole infinite continuum. Now, the question that confronts every researcher is, what's the best alpha? What's the best choice of tail thickness? In 99.99 dot something cases, the answer, by assumption, is 2. Well, that's not accurate. And as increasingly more of electrical engineers and others started to measure this, we have found that the alpha differs from 2. For example, Bell Labs did some studies on telephone interrupts and found that the best fitting alpha was 1.9. But that's a very different model, 1.9 or 1.8, than the model of the textbooks. If we look at the internet traffic, the most recent estimates of internet traffic really plot out like 1.7. And if you use the old-fashioned variance measure that those of you with technical training had in your background, that would always be infinite. It wouldn't measure what's going on here. It only exists in this very simple, we call Santa Claus world at the top, where alpha equals 2. But the deep methodological point is this, that the distinction between normal and non-normal is not just fuzzy, which is quite clear, but it's quite relative. It depends on your bell curve. And a lot of stuff in the past that's been classified as bad behavior or abnormal very well may not be. Okay, you'd have to have a different argument there. As a technical point, with these kind of curves, I don't want to beat this to death, but there is something in probability called the central limit theorem. And the very adjective central tells you how important it is to that field. The central limit theorem says if I add up a lot of random things, I ought to get something that looks like a bell curve. And that's true. That's absolutely true. It's a mathematical theorem. It turns out, though, that's all the theorem says. Whether the bell curve you get has a thick tail or a thin tail, it doesn't answer in general. And in effect, to conclude that it's got a thin tail has been a non sequitur. So there's potentially a lot of malpractice out there. The social sciences, medical sciences, and the hard sciences on undue reliance on these thin-tailed bell curves, especially when you can go online now and get the software for free to check these other cases. So if you're a student and you're doing research in statistics, you always check the alpha. Okay, so with a better understanding of noise, let's talk about it. And what's really been, especially in my business, signal processing, a war on noise. Can we cancel it? Can we filter it? Here's the traditional image processing image of Lenna, who was a Playboy playmate from the 1970s. It turned out a researcher in my department at USC made an unauthorized digital scan of Lenna, and it's entered the public domain. I think Playboy was going to litigate this at one point. So Lenna's become the test case for many a lonely engineer on the latest image processing algorithm. As a story unto itself. I understand she still lives in Finland. The usual model is I take the signal like Lenna, add random pixel noise, and I get a noise-corrupted version of Lenna. And a great deal of modern research quite rightly concerns itself with trying to reduce noise. The noise is bad in an overall war on noise. And it comes right out of the modern Shannon era from 1948 when Claude Shannon introduced modern information theory, an attempt to get rid of noise, because in the limited assumptions they had available at the time, in that pre-computer age, noise really was bad, given those assumptions. Now look at this. Now here I've taken the Lenna image, and we start out on the far left. I have scrubbed out almost all the structure. And what I'm going to do on the second image, the second panel, is I add noise. I add noise at random, uniform pixel noise. And I think it's pretty clear that the image of Lenna is getting better, not worse. By adding noise, I've improved the signal processing, at least in your brain. If I add still more noise, more intense noise, a bell curve that's more energetic in effect, I have the third panel, and the noise is giving me still more features of Lenna. Now, if I continue to add noise, she washes out. So it isn't that noise always hurts. Sometimes it helps. And this has been a kind of revolution in the same way that our views of fuzzy logic and chaos being always bad have been a revolution. Here's a related image, another test case, not quite as sexy, not quite as popular. The famous baboon image, I start off with a scrubbed down image. I add a different kind of noise to this. I believe in this case it's the infinite variance Cauchy noise, and you see the same effect. The baboon's image gets sharper and sharper as the noise goes up. That's completely contrary to 200 years of physics and engineering. Add more noise and it does go down completely consistently with 200 years of engineering. So what is this effect when noise goes up? The term from about 20 years ago, an unfortunate term, in the same way that fuzzy logic was an unfortunate term, called stochastic resonance. And it's often neither stochastic nor resonant, and we just call it SR. More generically, it's a noise benefit. And the upshot is this kind of curve, this signature of stochastic resonance, where I have the intensity of the noise on the bottom or horizontal axis. And as I move from left to right, the noise is getting stronger. And on the vertical axis, some measure of performance, in this case, a signal-to-noise ratio. And sure enough, for most of the time, after the dashed red line, noise does make things worse. But at first, noise greatly enhances a signal. And that's usually the case for faint signals. And if you think about this, we're living in a world, and the natural selection setting is that world, where we're surrounded by lots of faint signals. And noise is a way that we can use, and nature is found to use, to improve our detection of signals. It has an interesting history. I'll talk about a couple points. First is what's called dithering. A lot of control systems engineers and others came up with this as far back as the 20s and 30s, and more popular terms, and more recently in the 60s and 70s. The first panel shows a sine wave, that ideal frequency, that ideal narrow band frequency, and the sine wave is wiggling between two dashed blue lines. And if I'm taking measurements at those two black dashed lines, I can't measure it. The signal isn't strong enough. But in the second panel, part B, if I add random noise to the sine wave, then I help it jump over the upper threshold, blue, and fall below the threshold, and that gives me the result in C. So I get some spikes, if you see, in C that come from clipping the signal. When I energize through noise, when I dither that signal, I end up with a spike sequence where the peaks and troughs tend to correspond to the peaks and troughs of the sine wave. Now, this kind of thing has been around for a long time. The underlying results, mathematical reasons for it, we're still working with. I myself have contributed to it, and something called the forbidden interval theorem. If you're interested, you can go to my webpage of all the papers there for public access. There's another application of noise, though, that's even older. It's a great story that really justifies an entire talk unto itself. I assume most of you have seen the great 1949 Cecil B. DeMille movie, Samson and Delilah. Everybody seen Samson and Delilah at the end where Samson pushes the pillars and the god Dagon falls. Delilah, considered by many at the time the most beautiful woman in Hollywood, was Hedy Lamarr. Now, what's stunning is to realize that Hedy Lamarr is a co-author of the first patent on the constructive use of noise. That's just a stunning fact, a fact that's not gotten anywhere near the attention it deserves. And how could that be? A lengthy discussion of this in the book. It turns out Hedy, who came to fame in the early 1930s when she posed nude in a Czech movie called Ecstasy, which you can find clips of on YouTube. And, actually, it was on the Turner Movie Classics a while back. They ran that. And she married an Austrian arms dealer named Mendel. And both Hedy Lamarr, or whatever her name was at the time, and Mendel were Jewish. And in the 1930s, her husband was in thick with the Nazis, and in particular in their latest discussions of engineering and war devices. So she quite likely knew Adolf Hitler, quite likely tipped the glass with Adolf Hitler and his crowd. She flees from Mendel in the 30s, comes to Hollywood, gets a contract at Warner Brothers, and becomes famous forever thereafter. But along the way, she brings with her an idea, or she has an idea to use noise to make it harder to stop a torpedo aimed at a sub, was her idea. So this came up, she'd seen the militarization of Germany and Austria, and the question is, how did she get that idea? She had no formal training in engineering. On the other hand, if she simply overheard some German engineers talking about this, we've got a problem, because the German engineers never did this kind of thing. And we should have seen some kind of evidence of that. She teamed up with George O'Toole, a conductor and avant-garde composer, and they filed this patent. And you're looking at it, you can also go to the patent office. At the heart of this is something called frequency hopping spread spectrum. You have to understand, your cell phone uses this, uses some form of this. And the idea is essentially this. If you look in this figure 4, you see a kind of a roll. That's like a player piano roll. Let me just give you the idea. Suppose I want to transmit a signal using Morse code, just dots and dashes, just a duration. I could take an organ, or piano, but take an organ, and pick a particular key. I could take middle C and just make the dots and dashes, okay? Now, what I could also do, though, is take that same code, and each time I hit the key, each time I enter a dot or dash, jump to another key. I could jump up to an A or down to a B flat and so forth. And that would be hopping the frequency. And I can do much more than that. Suppose for each time I have a dash, I want to add some redundancy in case there's noise in the channel that would corrupt this. I might say each dash, repeat it 5 times, each dot, repeat it 5 times. And for each of those, I can jump around different keys. And if you were to come upon that all at once, it would in effect sound like all the keys being pressed. It would be a form of, in this case, very faint white noise. But you wouldn't, by zooming in on one of the keys, you couldn't detect the signal I'm sending. You would occasionally just get a noise pulse. The idea of the player piano captures that scroll. That scroll captures that idea of jumping the frequency. And again, it's something we do to this day. I myself have a patent that ultimately relies on this. It's the first fuzzy logic patent for generating frequency signals. But that came out in the 1990s. This is the 1940s. It was a black patent at the time. It was kept secret for many years. The Navy and others did rely upon that, and of course the patent ran out after the 17 years. Today it's 20 years from date of file. Many years passed, the digital age came about, computing power made a lot of the algorithms more feasible, and we get modern wireless technology. Shortly before she died, Hedy Lamarr was given a prize, an inventor prize from the Electronic Freedom Foundation, and her famous words were, quote, "It's about time." Okay. But the idea that she had introduced, very radical idea, that we could take a signal and hide it in the noise. It really becomes a form of noise. I mean, as we speak now, a lot of those wireless signals going through your body are spread signals. And there's a big gold rush about what's the best way to spread it. But the idea commences with her. There's no question about the documentary record. Again, I discussed that at length in the book Noise. Modernly, SR applications are great in nature. The idea came from some physicists in Italy, again about 20 years ago, an attempt to explain the Ice Age periodicity. It's been applied in thousands of cases since then. Just list some of those here. I want to show you some quick ones in the interest of time. If I take a narrowband signal, like a sine wave, like playing middle C on the piano or on the organ, it looks like the input signal. And depending upon the nature of the system, now it has to be a nonlinear system. A linear system is like a sheet of paper, if I plot it. A nonlinear system is like a crumpled sheet of paper. Only a nonlinear system can benefit from noise. Not all nonlinear, but only if you're nonlinear. And what happens is if I don't add enough noise, in this case, to something called a quartic bistable nonlinear system, I get the plot in the lower left corner that really doesn't replicate the signal. If I add too much noise, I get the far right, and it just looks like noise. It has to be that Goldilocks, just the right amount, the optimal level of noise, and I get the case in the middle where the peaks and the troughs sort of look like the sine wave. Now here is Procambarus clarkii, the crayfish, crawdad in Louisiana. You might have eaten crawdads before. There's been a lot of study of the noise effects of this freshwater creature. Why? Well, because this says a lot about life, doesn't it? You think you've had a hard day? I was thinking when I look at this picture. This is a largemouth bass. You see why it's called largemouth bass. The most popular freshwater game fish in the United States. Second most popular is rainbow trout. And its favorite thing to eat is a crayfish. So if you're a crayfish, you care a lot about detecting largemouth bass signals. And what might that be? Well, the bass, how would you detect, again, we're talking about the effects in water, how would you detect that? The bass wiggles in a characteristic way. The bass has, in effect, a sine wave that gives away its presence. So it's in the interest of the crayfish to detect that sine wave. There have been a lot of experiments. Its brains, in effect, are distributed in a neural way throughout its tail fins. And it's trying to detect that sine wave. And the current in the water or the turbulence in the water, studies have shown, acts as a kind of noise. And if you don't have it, it doesn't detect as well. If you have too much, it can't detect anything. It's more likely to get eaten. And if you get it just right, well, you get the noise benefit. So there's pretty good evidence here on this sense that nature, having had eons to tune our signal processing parameters, has taken advantage of the local free energy, which is otherwise wasted as noise. A different kind of broadband case is Jiminy cricket here. Now, a cricket, a lot of its neural stuff in its stomach, neurons, and it's trying to detect broader band frequencies in the air molecules colliding, and it's really worried about a wasp, which stings it, keeps it alive, lays its larvae in it, and then the larvae hatch and eat it alive. So it's trying very hard to distinguish the back and forth sound of the wings from the colliding air molecules, and the wasp is playing a game trying to hide behind that, back and forth. And some researchers at Berkeley found that to a first order, the cricket appears to be using the noise in the air molecule collisions to help it detect the wasp. It's not definitive, but it's a fairly strong empirical example. Another case has to do with sharks and rays, and these black pores you see are the ampullae of Lorenzini. They're gel sacs that are really passive electroreceptors. You may have seen on Discovery Channel, you can bury a device emitting a low current under the sand, and the sharks can come right up to it. And we all emit through thermal noise a spectrum. For example, a rattlesnake can see us in the infrared part of that. And sharks, ideal signal processors that they are, appear to use the local noise in the water. But the only good test we have is the oldest known animal in America, 300 million years old, the paddlefish. And this is from the Midwest in Missouri, where they still have an open season. It's like a sturgeon, and its roe is often used for caviar, as a substitute caviar. The big paddle used to be thought as a paddle. It isn't. It's a big antenna, and it's full of these ampullae of Lorenzini, and it uses that to detect little tiny zooplankton, which it soups up through its gills. Professor Frank Moss at the University of Washington in Missouri conducted this experiment and reported in Nature. Put a paddlefish in a tank and looked at the electric field that the prey generate as a kind of defense mechanism. You see examples of it here. And he and his colleagues showed that if there were no electric field, no noise from the prey, the paddlefish didn't do as well at detecting the prey. If there was too much noise, it also didn't do as well. If there was just the right amount, it got dinner, so to speak. And so these evolutionary arms races between prey and predators seem to be sculpting and retuning noise parameters. Your brain, 400 billion neurons, and the neurons throughout your body constantly bombarded by noise, all kinds of chemically based noise from other non-neuron cells like glial cells. Just the sheer effect of crosstalk from so many other millions, hundreds of millions of neurons in a network talking constitute a form of background noise. And we've got a lot of evidence now that in that case we have a benefit from noise. And in particular, we can take that and go all the way down to the world of nanotech. Terry mentioned nanotech. It certainly is the way of the future. And I'll report here a fairly recent result. On the left is the ideal case of nanotech, a nanomolecular gear. On the right is more the real world, what Brownian motion tends to look like. In this case, like a grain pollen being buffeted about by colliding molecules. At the level of nanotechnology, as we make chips smaller, the noise is intense. It'd be like trying to put on a roof of your house during a hurricane. It's very difficult to construct devices that work at that level. But I and my colleagues and students found a mathematical result that said neurons that act like simple switches are guaranteed to benefit from noise just in case a technical result holds, which is fairly satisfying. And it was pretty clear that we could find examples in nanotechnology that did that. Let me illustrate this one more point. You see the bouncing around here on the right. If you plotted out the path of the blue ball, it should look like the top plot here, which is Brownian motion, a Brownian jitter. And even here too, just in the case of the bell curves, we found that the real world is richer than that. Really, we've got more general, not Brownian diffusions, but what are called Levy diffusions, after French mathematician Paul Levy from the 1920s. You see on the second plot, you see big jumps. And so it's like a Brownian motion, but different. And that's the very frontiers of science. Now, if we look at the nanotech world, the workhorse of nanotechnology today is a carbon nanotube. They look like chicken wire rolled up, about 1/100,000th the thickness of your hair, carbon atoms, and the ends of the caps of them look like a buckyball or a soccer ball. All kind of wonderful properties. They appear to be the best electrical conductors that we have. Very strong, 50 times or so stronger than steel. You can put them into long fibers and get nanowires. There have been talks of constructing space elevators using these types of fibers. This is the way of the future. I have to tell you, if you look at the patent office on these, there's been a gold rush here of patent filings of several companies, I believe some in this area, attempting to use carbon nanotubes for transistors and new chips and the like. There's also been a dip in that, but the research goes on. Depending on how you twist the carbon nanotube, this big molecule. Remember, diamond is just also a big molecule of carbon, but structured in a different way. The twist might give you a metal, or it might give you a semiconductor. When I looked at that, and I'm certainly no expert in nanotubes, but it was clear to me, looking at the plot on the right, that the nanotube, at least within a certain range, acted like an on-off switch, acted like this neuron does on the left. And armed with a new mathematical result that on-off switches are guaranteed to benefit from noise under very general technical conditions, I made a conjecture. The conjecture was I could use a carbon nanotube to detect a very faint signal, it's a kind of real tiny antenna, and improve its performance by adding electrical noise. And that's why God created graduate students. We set about testing that hypothesis, and the students working late in the labs, and it was complicated. Look, I don't have an atomic force microscope, but one of my colleagues does, and we had to use it on the weekends. Here you see on the right the actual tube lying between a gold titanium electrode and an elaborate setup. This is all online, you can look at it. But the upshot was it worked. Here's a report out last year in the Transactions of Nanotechnology. The curve, that's a complicated slide, and this is just for glancing purposes, but you get the characteristic inverted U curve of stochastic resonance of a noise benefit. Now, to give you some sense of which that can apply, you can create, and many folks do, entire arrays out of carbon and non-carbon nanotubes, inorganic nanotubes. In a cubic inch, there could be trillions of these. And those could, for example, be used in clothing. They could be used in housing structures, and in general as intense antennas. For example, we could use these to replace maybe, or clumps of these to replace some of those hairs in your inner ear that get degenerated by noise over time. The trouble with working with arrays of tubes, and we were working with colleagues at JPL, the Jet Propulsion Lab, is they get meshed up together. And once a couple tubes lock together, it's very hard to unlock them. A lot of research is working on that. But by changing the length of the tube and the chemical bath of the tube, you can change its signal processing characteristics. It's the way of the future, or at least one way of the future. Let me wrap up here because I want to get to questions. So in particular, we call this nanosignal processing, working with nanotubes. One example would be an artificial cochlea, where at least some of those hairs are replaced by nanotubes. I want to also point out, a lot of my colleagues have shown, and in LA at the House Ear Institute, that if you have people who are deaf or near deaf, in some cases you can actually, if they've had a cochlear implant, an inner ear implant, oddly enough, you can improve their hearing by adding noise. As I gave a talk once there about noise to people who were using noise to improve their hearing. It was very self-referential. Noisy quantum computation. Quantum computing is a hot field. Many of you will be going into that who are students. Among other things, it allows you to do massive computations in parallel. It's also used for security purposes. I believe it was the presidential election in Switzerland recently used a quantum-based device for security purposes. Still, quantum computers are a long way off. It was a big deal to factor the number 15 into the product of primes 3 times 5 channel. Another area where a lot of research is going on, and I'm going to conclude on this, is Brownian motors, or Levy motors in general. A Brownian motor is a little model that benefits from noise locally. One model would be the kind of ratchet you see on the lower right. Noise buffets the paddle. And in general, it will turn it to the right or to the left. As random molecules collide with the paddle, it can go either way. But if I can set up a ratcheting device to rectify it, to only let it turn in one direction, then once in a while, when enough molecules collide, I'm going to turn to the left and stay there. And I'm converting energy into motion. I have a little motor. And over time, with enough collisions, I could have that kind of rectified motion. Now, you have to be careful here that you don't end up with a perpetual motion machine and violate the second law of thermodynamics. One of the more exciting areas of noise research, there's many of them, is in biochemistry. I have myself some students looking at this, where there's pretty good evidence that in your body right now, and those 10 trillion cells, that there are little protein engines, in effect, protein motors, kinesin and myosin and others, that use noise in the form of a Brownian motor. In effect, these devices walk hand over hand. They're transporting goods in and out of the heart of the cell. They grab hold, and the other hand randomly goes around through noise till it finds a good place to grab. And each time it grabs, it burns usually one molecule of ATP, adenosine triphosphate, the basic unit of currency of energy in the human and animal bodies. So if it weren't for that, we would have a kind of free ride. But every time, in order to get the motion in one direction only, to harness the randomness, you have to burn up a certain amount of chemistry. So this is proposed as a potential answer to what is the secret of life? Answer, noise. In the sense, going back to the most basic notion of life as animation and very tiny things wiggling, sperm motility, for example, where does the motion come from? At that level, these structures are being buffeted by intense quantum winds, Brownian motions, Levy motion. It's hard to believe nature wouldn't hitch a ride. Again, there's no free lunch here. But if you could combine an external energy source, in our case, in our cells, ATP, adenosine triphosphate, you can get directed motion. And so in that sense, noise animates us as well as irritates us. I'd be happy to take questions. Thank you. We have microphones. It's a free fire zone. Go ahead, sir.
So now when we're looking at statistical distributions, we've got to be worried about alpha as well as classical sorts of things where you're looking at standard deviation and mean.
Yes, you do.
So how many, with classical distributions, you've got a square root of n type of thing to estimate how many data points you need to get a given accuracy. So how many data points do you need to take to figure out an alpha?
That's a good question, and the square root of n property does not hold in that case. Let me cast it this way. Modern science and engineering uses about 15 to 20 probability distributions. The Gaussian bell curve is the most common. And you might ask why. And one answer is people like Gauss discovered them. They're easy to write down. But it doesn't mean nature uses them. This is the key point. And the analogy I like in this case is that of the drunk looking for his keys. It's on a dark street. The drunk is under the lamplight going round and round the lamplight. And the cop comes along and says, "What are you doing?" "I'm looking for my keys." He said, "Well, where'd you lose them?" He said, "I lost them over there." "Then what are you doing here?" He said, "Well, this is where the light is." In the same way, we shoehorn people into thinking of these small numbers of distributions that have a square root of n effect. The other ones don't. And we're trying to get away now from making assumptions about the data to letting the data tell their own story. So it'll go up with n is the answer.
Yeah, sort of what I'm trying to get at specifically in making integrated circuits.
Yes.
You worry about how noisy your lines are because if you assume a Gaussian, well, 8 sigmas out is where it kills your microprocessor.
That's right.
Well, in actual point of fact, if you have a Cauchy distribution, then trying to estimate how much deviation you're going to get out of a billion samples from 20 is completely inaccurate. So I'm trying to figure out how many more you would need to take before you could say.
Yeah, and that's a case-by-case basis. But even slight deviations from Gaussian, far less than Cauchy, require a fair number of samples and will produce very different observed noise effects. Thank you. Next question. Upstairs, yes.
I'm interested in your correlation between social norms and noise management.
Yes.
Do you have any thoughts on any examples of cultures that have successfully managed noise as a social norm? And can you comment on what you see as the benefits to the society for that?
Well, I think the easy answer to that is our great ancestors. You know, modern times consist on the order of about 10,000 years or 500 generations. But if you go back to where our neural chassis were sculpted and the great amount of time of hunter-gatherer, it was a delightfully quiet environment. It was a low decibel environment, and to which our systems and our mammalian ancestor systems were adapted. So when there was a big decimal, a loud event, it usually had to do with survival, a scream, a thunderclap. It was something that could damage tissue. And today we've inherited that adrenal system, and when you drive to work on an LA freeway, let me tell you, it's something very different than our hominid ancestors had to face. So I think almost all of classical human culture lived in a relatively quiet time. And other than some so-called primitive cultures today, I don't think you can find that because people tend to live closely together with modern devices. It gets noisier all the time. And where it's headed is unfortunately more of that. So one thing you can do is to be a good citizen and wear headphones and just be smart about that and keep them turned down for your own sake. Yes, sir.
I'm rather thunderstruck at the idea of noise being a positive force to bring things into focus. And I'm wondering if you had thought at all in terms of genetic variability with the fitness landscape, you know, that you have a baseline genome and that noise would actually play into, you know, the fitness landscape.
A question many of us have looked at, and we were trying to figure out how did this crayfish that we're looking at, and we'll still see, how did it tune its parameters over epochs of history? And if you model things in a genetic algorithm, it's called, and you try to climb Mount Improbable, as Richard Dawkins put it, well, Mount Improbable looks differently if you've got different kinds of noise types. The noise may or may not help, but also the kind of noise may or may not help. But the key thing about noise is its energy. Usually it's a nuisance, but not always. And it's those not always occasionally that might get you up to Mount Improbable. But that's really an open question. Don't be bashful. Let's get to the mics. Go ahead.
Why does noise affect mood?
Does it affect what?
Mood.
Mood. Makes us cranky, doesn't it? It does. My opening line of the book, Noise, and I really mean it, is I hate noise. Just hate it. It undermines your sleep, which in turn can undermine your overall sense of well-being. Over time, average, it can affect stress levels, apparently increase the risk of heart attack and stroke and all those kind of bad things. But again, when you get, especially a loud noise, but any kind of noise, but a loud impulse noise, a Cauchy type spike of noise, you get an adrenal response whether you like it or not. We were adapted to a low decibel environment, and that is not the environment in which we live today.
I was talking more like music. Why does different music make us either happy or sad? Or
well,
why does it affect
I wish I could answer that. That's always been a hard problem, and as a musician myself, is you can listen in a good mood to very somber music. You can listen to funeral music, for example, and enjoy it, and contrary-wise, be in a bad mood and listen to upbeat, major scale music and enjoy that too. The matching of the arousal system with the cognitive state is a complex one. But I do want to say on that point that noise often can, at least I find, it's hard to pin this down to study, help you think a bit. Sometimes if you have no music playing in the background, for example, I find at least in working that's a hindrance. If it's too loud or if there's voices in it, but for me, symphonic music adds stimulation. And I just give you a real quick anecdote. When I took the infamous California bar exam, I just wanted to see if I could do it more than anything else. It's a nasty 3-day exam, but there's a new documentary out about it called A Lawyer Walks into a Bar. You might take a look at it, because it was based on the same setting I had. And on the first day of the bar, it's 3 days in California. It's the toughest bar in the nation. The first day is a bunch of essays, and you're waiting until 9 o'clock to say go. And I point out 61% of those took it. When I took it, failed. I passed. You didn't know that at the time. And suddenly, when the proctor says go, and all these keyboards start flying, there was a magnificent noise hum of all these hundreds of fingers, including mine, scrambling on the keyboard as fast as they could, and it produced a kind of gentle background sea of noise. It was really energizing. And it also had the nice effect of masking, and I also didn't have a lot of sleep, so it helped keep me alert, of masking background noises, people tearing open their packets and doing all kind of things, and I happened to sit next to the restroom, and they were walking back and forth. Now, on the second of the third day of the bar, it's multiple choice only. And it's 100 questions in the morning and 100 questions in the afternoon, and they're nasty ones. But those questions are done with pen and paper, so it's very quiet in the bar, unlike the essay sections, which is this frantic typing and this quasi-white noise envelope that we have. And there was very different. It was not energizing. You could hear a pin drop, and every time someone walked back and forth, we could count the steps. So a bit of noise background, for me at least, and many others, does help us think, does help us concentrate. Yeah, very good. Yes, sir.
Have you examined the effect of noise in quantum mechanics, like quantum tunneling? Stochastic amplification that you've mentioned before seems to be like a form of tunneling. Yeah.
Some folks have. My colleague Peter Henge has in Austria, and others. We looked at quantum communication, which is a little different kind of thing. But tunneling has been a candidate. There have been some studies published, theoretical models, and often you simply plot the inverse curve and call it quits. But in terms of an actual proof, a mathematical proof, that's true if and only if 1 + 1 = 2, we've only got that for a quantum communication setup, which is a little different. It's odd, it squeezes light and it sends chunks of compressed vacuum for ones and zeros, but it's not quite the same thing as tunneling. But other people have looked at that. Very good. Yes, sir.
Assuming an extraterrestrial civilization is sending out signals like ours, what would the possibility of detecting those signals be like if you've given that any consideration?
I'm sorry, the probability of?
Detecting the signals from light years away.
In terms of noise effects?
Yes.
One thing is the tendency we have to discard noise as noise rather than signal. And that comes back to this assumption of how thick should the bell curve be. Am I going to say if it's 2 or 3 standard deviations, the usual rule of thumb is beyond 3, it's error? Maybe that's ET talking to us, you see. So there is a concern, and there's only so much you can do, and the search is doing the best it can with the resources that it has, that the distributions and the assumptions may blind us, and there's a great faintness to the signals. I heard a recent calculation that our expanding sphere of television signals is so faint after 60 or 70 years that to detect them even 100 light years out would be very difficult to distinguish that from different kinds of faint white noise. So I'm sorry, at the top, go ahead.
Can you explain how noise-canceling headphones work?
Oh, yeah.
And whether those are healthy for your ears?
Well, as a lawyer, I'm hesitant to say whether something is healthy. So let me, and I'm outside my jurisdiction. So noise-canceling headphones, I'm actually teaching a class, adaptive signal processing on Wednesday, where most of the students do noise-canceling projects. The idea is to match trough to peak, and if you can take one wave and find its sine wave and its offset in phase other wave, they add together and you get a very light hum in the background. That's the ideal thing, cancellation of the two waves. The noise headphones, and I discuss this at length in chapter 5, comes out of the work by Professor Lindaris and others in neural networks, in particular originally the work of Professor Bernard Widrow at Stanford. And the idea is that we have schemes in the signal processing for tracking the shifting probabilities and the shifting noise. And we real quickly build a model of the noise and then subtract it off from the actual noise. That requires taking two measurements, one measurement near you and a measurement a little further away for a noise device. And some of these are very sophisticated, like for pilots. And I had a student develop a system for helicopter pilots, because there's many different kinds of noise that you have to cancel if you're riding in a helicopter, from the rotor, from the main blade, and from other things inside. And you have to keep tracking the noise, which not just is random, but has its own shifting probability characteristics, and again, subtracting that off. Another student did a project on this, doing skydiving. So you can buddy wrap. Also, the students get a lot of free things when they go out doing a project. So went out to Moreno Valley in California, a lot of skydiving takes place, did a buddy wrap several times, and the question whether he could speak to the expert, and as they dropped in free fall and cancel, and they could if you built the model. So the headphones add a form of noise, in effect, to answer the question. And that noise is exquisitely calculated based on what else is coming in. Now, something like that is done in echo cancellation on phones. If you've spoken to someone long distance, we have to bounce that light up to a satellite, and they're maybe in Australia, and it's got to come back. There's a lag there. And if you weren't careful, you would always have an annoying echo. But the nature of the echo depends on the signal. We've got to track that real fast, and computers are fast enough usually to do that. So if you can track and sample the signal fast enough, you can build it and kill it. And that's what noise headphones do. If the noise you're trying to cancel is very loud, it will be a big background hum in your ear, but it may be better than nothing. My own experience is they're quite enjoyable. Their health effects, no comment. Another question?
A question about your advice for young people as they move towards professional life,
Yes.
sciences and otherwise. Introduced as a Renaissance man, certainly demonstrated by your skills and experience in music, law, and of course the sciences. What do you see as the value in being as broad, eclectic, and as yourself towards versus the increasing pressure to be specialized
Right.
for people in sciences?
Of course, the value is to arbitrage, to make connections between fields, and most of the technical fields are very similar. For example, you use different language, and so occasionally you get points of value. But my advice to a student, and you may not want to hear this, you want to be good and you want to be the best, and if you want to get good, there's an easy way to do it. In theory, just work a lot of homework problems. Now, I know that may not be fun. It's a pill that's difficult to swallow, but if you want to get good at any subject, you don't have to be a student to do this. Pick a subject. I do this myself in other fields. I love that effect of training. I'm kind of addicted to it. I still practice bar exam questions just to keep in shape. Even though maybe also the horror of going through that, I haven't quite shaken it. But I work, for example, I start my day, have for 6 years, every morning as I shave, doing at least one problem of a field of mathematics called topology. That's the first thing I want to hit my brain. And if I didn't do that, that knowledge would decay. But by doing a problem of topology per day, it's like an apple per day for the brain, it keeps me sharp for that kind. And so it's a relatively easy way, I think, to master any subject. You've got to do it. It's a hard work, and the world is is a complex place with lots of competing things. So the opportunity cost of doing one more homework problem when you could be doing so many other things is not there. But if you can align your interests with that thrill that comes from knocking out a problem, the world is yours in any field. Things are specialized, they have to be, but if you really can't get this stuff at the spectator level in any field. You got to get your hands wet, and you got to get into getting your hands wet. One of the, I think, big unintentional mistakes of our educational system is early on, 3rd grade or earlier, we associate homework with punishment. And that's exactly the wrong reinforcement. So, for example, in my classes, for what it's worth, my small contribution to pedagogy is I always make homework extra credit. You don't have to do it, and everybody does it because it's kind of pure profit. But I don't want it to be a negative. It's a way of sharpening your brain, and that's one of the most important things you can do in any field. Yes, ma'am. Thank you. I'll give a quiz will follow after this.
As a fellow musician and actually an organist myself, I've been kind of going off, doing a little bit of extra study on how to protect our bodies, including our hearing, because that's people in my field, we tend to overblow our ears with music. How does the temperature of air, since air is supposedly, or at least technically, lighter pressure as the temperature rises, kind of going off of what you said about that water takes the sound so much farther than air does. How does temperature relate, and does it make a huge amount of difference, both hot and cold?
Right. The answer is no, it doesn't make a big difference. Again, just because water compared to air is so much more efficient. I think it's something like 20 times more efficient in transporting heat away from the body. And if you do that, I like to snorkel. And if you do, I can't do it here unless you have a wetsuit. But if you go to Hawaii, you can tell a change of 1 degree Fahrenheit in the water, whereas in the air, it's not quite as easy to do that. A great way to burn fat is simply to fill up the bathtub, let it equilibrate to room temperature, if you can stand it, and get in there for 30 minutes. The physical transfer, one study I heard is something like 500 calories per half hour. You'll be shivering, and eventually you'll suck all the energy out because a lot of your calories are used with that. But comparing air and water, so a temperature change in the air, not much in terms of the sound level. If it were water, very much. So, yes, sir. Oh, go ahead. I'm sorry.
Your bell curves, I couldn't see being older. In addition to losing my hearing, I'm losing my eyesight. Your bell curves, what was the horizontal axis? Was this a power, or 0 is 0 power, -2 is what? Just a little confused on the bell curve.
On these bell curves here, the horizontal axis for the noise benefit was the strength of the noise. For the earlier bell curves, it was simply a number between, say, 10 and -10, which we'd pick at random. And by the way, one noise effect is optical noise. And this is something else we haven't evolved for. I'm staring with lots of lights in my eyes, but we all encounter levels of photon exposure that our ancestors didn't. And so there's a real question of whether the way our system works with photopigments isn't just getting exhausted, and the effect that has not just on eyesight over time, but the brain. And we just don't know. Yes, sir.
I was wondering if your field of study is going to benefit from the absence of analog broadcast.
Yeah, it is kind of sad to see the analog go away. One example of an analog versus digital difference, I can mention indirect response to that I talk about in the book. A lot of concern, especially in light of stochastic resonance effects, of whether holding an electrical device like a cell phone to your ear so close to your brain can affect your brain. In particular, could you increase the probability of getting cancer? And as you can imagine, not just the lawyers, but manufacturers are quite interested in that question. In 2004, there was a study out of Sweden that looked at effects of for 10 years if you used analog cell phones for 10 years. So they didn't really have digital cell phones in wide usage. And in that case, they found the incidence, using what's called a logistic regression, the incidence of acoustical melanomas, of acoustical benign tumors on the auditory ear, on one of the cranial nerves, was 4-fold. If I always held the cell phone, the analog cell phone, for 10 years or more, not for less, to my left side, it's 4 times more likely to have a benign tumor on the acoustical nerve. Now, whether something like that goes over to the digital age, we just don't know. And IEEE Spectrum and other places often publish where we stand, and we're looking at a case of where we can't reject the null hypothesis. It's too soon to tell. And further, if it's a case that there's a stochastic resonance benefit, many have argued, just theoretically, not on any particular evidence, that maybe you could get a unintentional noise boost and maybe get a gene to click on or off like a threshold switch that wouldn't otherwise have done. And so we'll just see. Otherwise, in the loss of analog, I don't know. I think in the end, everything we can do with analog, we can or soon will be able to do with digital. Another question? Yeah, at the top. Good.
Yeah, I hope I can articulate this. When you had that graph on there with the sine wave, and you add noise, and it
Right.
bumped up the energy enough so you could read the darn thing.
Right.
I'm thinking in terms of statistics and economics, being able to add noise to data points so that you can tease more information out of things that, masses of data that look random. I just know that we're just getting much better at teasing information out of masses of data that we can now do. We couldn't maintain this data or keep track of this data 30 years ago. With computers, we now can. Can you tell me kind of what your thoughts are on that? How would you add noise to data points and economics?
That's a great point, and in econ and elsewhere, a lot of us have been looking for stochastic resonance effects in the derivatives market, for example. And also, there are many results that came up in the work of researchers in neural networks that found if I trained a neural network to do a certain problem of pattern classification, for example, to recognize your face in an image, I could get a better result if I added more information. Well, I often don't have that information. And then they found that if instead of having that extra information, I simply added noise to the samples and ran the simulations, I got the same result. So it's been an odd effect, never really explained, a lot of us looked at it and tried, where noise creates kind of simulated data. And that's very much in the spirit of what's called bootstrapping, not the same thing, but bootstrapping in the sciences, where we take the given data set, and instead of using it once, we sample from it millions, billions, trillions of times, and often can suck more statistical juice out of those extra samples. And one way of doing that is a type of dither, or adding noise. It's also done in other cases in engineering to smooth out effects. For example, when you go from analog to digital, like in a music CD, there are bottlenecks there and all kind of defects. We get away from that by adding noise in different places to smooth out the signal, very much like getting that sine wave to go up and below the thresholds I had before. Yes, sir.
I was wondering, how fast can sound move? I know that it moves faster through water than through air,
yes,
and faster through granite than through water. So how fast is the top speed that sound can move?
Answer is, I don't know. I really don't know. 5 times faster than on average in water, subject to a lot of conditions about temperature and pressure. And that's an empirical question that a lot of people look at. I'm not one of them. It's a fluid mechanical question. It's a good question. Go ahead.
The optical noise going from LCD, from the old TVs to the LCD TVs.
Right.
It's like the same thing with the cell phone.
In the sense of this kind of image.
Well, there's something that in the TV signal, the old TV signals, they found with the repeat rate, it's resonating with a bunch of brain cells. It's like I know you have to repeat it.
All right, Terry had a question on the order. What's the effect when we go from old TV type signals to modern LCD? You do get a different noise structure. And by the way, something you don't get is often the digital cables. You used to get in the old-fashioned TV sets a real, what was called a Markov random field. You could turn on channel 53 or something and it just was snow and pure pattern, a kind of a spatial, ideal white noise and spatial noise. We've eliminated that. I don't know the distinctions of that. I know it's a finer level of noise, and there still is some noise added to those in the digital case to smooth it out as a signal processing technique.
Okay, let's say thank you.
Thank you very much. Great to be back in Portland. It's been a pleasure.